Okay, so let's continue where we left yesterday. Just I wanted to give few references because I was asked yesterday. I see a lot of people taking notes. Most of what I'm saying and part of what Lenka is saying is actually something you can find in a long review, which you can find on arXiv. This is a reference. It has been published in Advanced in Physics this year. And, well, pretty much everything I'm saying is in it. So you are welcome to consult it if you want some reference for this lecture and part of Lenka's lecture. All right, so where were we yesterday? We discussed a problem of statistical inference, where we want to learn some numbers by looking to other numbers. Schematically, what we did was looking to a problem like that. There was a vector x, we observed a vector y, and we try to infer the vector x from the knowledge of y. Now, of course, you can see this in the paradigm of information theory as some kind of or correction or decoding. For instance, in communication, the way you think about communication is that you want to transmit a vector x. This is called a channel. And you are receiving y. And from y, you are trying to decode. So in this language, it's called decoding. Okay? So the difference in the two applications, I mean, this is pretty much the same thing, actually. I mean, the problem in decoding in communication and the problem of inference in statistics, except in one case, which is the coding one, you can decide what x is, or you can decide the dictionary of x. It's called the code book, so that helps a lot. While in the case of statistical inference, you have a priori no idea about this guy. But otherwise, this process of decoding and of inference is very similar, and in fact, it's the same technique that I used in both cases, is map, maximum likelihood, maximum a posteriori, and even this belief propagation that Lenka was discussing. Okay, so I want to use what we said last time now and to give a concrete example of a problem which you can think of as a coding problem or as an inference problem. Okay, so here is the problem. Let me first state it as an inference problem. So imagine you have a group of n people, okay? And let's say that these guys divide in two different groups. Each of them are, I don't know, friends, okay? Or maybe these are like people who like two different teams in sport. So let's say that you have the one guy, those, and you have the minus ones. Right, so two groups of people. Now, you would like to know who is in group 1 and who is in group minus 1. Well, actually, you don't care if it is group 1 or group minus 1. We would like to know who is in one group and who is in another group, right? If it is called 1 or minus 1 is in the eyes of the beholder, as they say. Now, what kind of measurement do you get? So in this game, what you know are friendship relations. So you know, for instance, that these two are friends, and that these two are not friends. So for instance, that's the kind of thing that you could, think about social media, right? You are Facebook, and you know that some people are linked together, so probably they are friends. Or some guys just don't like each other's post on Facebook, so they are not friends, something like this. So this is the kind of information which is available to you. Now, given all these links, right? So you have the white link, that, okay, these two are friends, and given the red link, these two are not friends. Your task is now to reconstruct the assignment for each of the persons, okay? So let's try to formalize this a bit. You have n values. Si is equal to plus minus 1. So let's call it Si star. This is the truth. if I is going from 1 to n, I will use small n. Right, these are unknown. And let's assume that there are as many 1 as there are minus 1s. So the measurement, these are also m values, so this is some of the unknown, the signal if you want, or the unknown. Now the measurement, what you know, you have access to m values, okay, which I will call j. For some pairs, not all of them, for some pairs, you know exactly what is j. In fact, it is given by the product. Right? Because the product is 1 if the two are in the same group, and it's minus 1 if they are not in the same group. Okay, so that's a bit too easy. So let's make it a bit harder. Let's assume that, there is some noise, because otherwise it's not really realistic, or maybe some people lie, or maybe there are some wrong measurements. So let's say that the information that you got is equal to that with probability rho, and equal to minus this with probability 1 minus rho. What it means is that you have some mistakes, right? So you are interrogating two groups of people. So are you guys friends or not? And with probability rho, they tell the truth. Say yes or no. And with probability 1 minus rho, they lie. Okay? And let's further assume that we choose this pair randomly. Okay, is the problem clear for everyone? So your task is now, knowing the j's, to reconstruct the s's. Okay, so if you want, these are the j's, these are the s. All right, that's a perfectly well-defined model. It's actually something that people have looked at. In this context, it's something called the censored block model. Now let me motivate it slightly differently from the point of view of coding theory, of communication. So one way of thinking of communication is the fact that you need to send the signal in such a way that when the receiver receives it, it can somehow find back what you really wanted to say. So imagine now you have a channel, that means something that is putting noise on your signal, which is flipping bits. So you can send some bits to someone, and some of them will be flipped. So one way of encoding a signal is to send the j's, right? You send, for instance, many value of j's, like this, to someone, and you ask him, okay, now do this decoding step, and find back the value of s. And somehow this is a way to send the value of the vector s. Okay? It's actually something that is called a sourceless code. And it's a particular version of something called LDGM in coding theories. It's a very bad code. Actually, it's not a good idea that I will advocate, but it's interesting to think about it because that gives you a nice example of what you kind of thing you do in coding theory. And just to tell you that this is exactly the same, right? I mean, you are receiving this, and you try to find back that. That's exactly the same problem as the one we have here. All right, so this is a problem we want to solve. Either we are a coding guy, or we have an inference guy, or a block model guy. We want to see how to do this. All right, so let's try to formalize this a bit. All right, so we are using now all the approach I have described yesterday, all this Bayesian approach. And in order to do it, first thing we need to write is what is the probability of J given S, which is what we called the likelihood yesterday. Okay, so this is not so hard. First of all, let me borrow now from Lenka. By selecting pairs randomly, we have created a random graph. That's exactly what we have done. Okay? And I selected m pairs of spin randomly, so I have created a random graph. The probability to generate a given set of j's, if you want, given S, since all the pairs have been done at random, is the product over all the ij's that belongs to the graph I have created of P, Gij, Si star, Si is J star. All right? Now we know what this is. I mean, Gij is just equal to Si star ij star with probability rho, and it's minus this with probability 1 minus rho. But somehow, there is a better way to write it, and this is actually one of the big truths when you write a probability distribution for a binary variable. You can always write it as in a field notation in physics. Okay? If you have something which is plus or minus 1, for instance, if P of x is 1 with probability rho and minus 1 with probability minus rho, you can always write that P of x is actually exponential of hx divided by 2 cosh h. It's just a change of notation. This is what usually we call a field. Okay? And if you want to go from here to here, so this is again assuming that x can take only 2 values, well, we need exponential of h divided by exponential of h plus exponential minus h is equal to rho, and exponential of minus h divided by one minus rho. All right? I mean, it is a triviality, but it's actually convenient to do it. Well, so I'm saying there is that, okay? And there is that. Now, if x is equal to 1, there's probability, P of x equal 1 and P of x equal minus 1. Right? So, just by identification, if it is 1, is that, this one is that, so they have to be equal, and the same. Right? So, you can always write binary probability as something that looks like something that depends on the field, and it is actually useful. So let's do it here. And I'm claiming that here, this thing is actually Pij. So let's see. For instance, if the two are equal, that means it happens with probability exponential of beta divided by exponential beta plus exponential minus beta. So if I use this notation, I need to have exponential beta right? So of course, this is valid only because J, S, and J and S can take only plus or minus 1 value. It's a triviality in that case. However, it's kind of cool to write it this way for obvious reason, because it starts to look like a stat phys problem. I mean, it definitely does. Okay, let's try to write a nicer relation here. For instance, For instance, if I do this minus that, yeah, we'll see about delay. Well, yeah. So the hyperbolic tangent of beta is 1 minus 2 rho. Is that correct? Right, if I do that minus that, here I get the hyperbolic tangent of beta, and here I get rho minus 1 minus rho. So it's actually 2 rho minus 1, I think. I don't like this at all. I don't like that, sorry. Give me a sec. Oh, that looks good, I don't know. That's exactly the opposite of what I have in my notes. So where did I go wrong? Oh yes, I remember. Because in my notes, this is what I defined. Sorry. All right, so rho is the probability of a lie. So I get the correct answer with probability 1 minus rho, and I get the wrong answer with probability rho. Okay, so in that case, 1 minus rho. Okay, good. And this is 1 minus 2 rho. All right, so I called this beta because, of course, it looks like a temperature, and I like things that looks like a temperature. But we should remember, I mean, this is just a proxy for using this probability of lying. All right, so this is all nice. Now that we have written the way to generate the problem, this is the forward problem if you want, let's try to write the way to solve it, the backward or reconstruction problem. And this we do by using the Bayes formula. We ask, what is the probability that the system was generated by a given set of spins, given that we observe J? All the J's. All right. So it's just all right, this is really just Bayes formula. Okay, now this is a probability distribution on S. So anything which doesn't depend on S explicitly, I can think of it as a constant. So let me say that this is just equal to 1 over Z. Okay, so first, this guy we know, it's here. That will be a constant, it doesn't depend on S. And here, well, let's assume that everything has been created randomly. So all possible assignments are equal. So P of S is just 1 divided by 2 to the n. It's a constant that takes the value 1 divided by 2 to the n for normalization, right? So I'm assuming a priori all the configurations are equivalent. All right, so if I do this, well, okay, this is a constant, so only this matters. This depends on beta, not on S. So things look exactly this way, which now we can rewrite like that. I mean, this is definitely, the posterior probability is definitely nothing but the Boltzmann distribution of a spin system, where S is plus or minus 1s, with an Hamiltonian. And the Hamiltonian should be very familiar. It's the sum over all neighbors on the graph, J, J, Si, Sj. So this is just the Ising model. with disorder, because the J's are not all equivalent. Some of them are 1, some of them are -1s, and so this is called the spin glass. All right, so of course this kind of model are really not new. I mean, we use it in physics since Edwards and Anderson. We introduced them in '78. So Edwards and Anderson introduced this model on a lattice in order to model, spin glasses, which are funny metals, which are basically useless but have interesting properties and funny properties. And the thing which is important to realize here is that, well, we have a spin glass. I mean, this is really a spin glass. So computed vest is really solving a spin glass problem. The geometry is a bit different. We are on a random graph, so we can do all the things that Lenka taught us in the first lecture. So that's why we switch, actually, so that now I can use directly belief propagation. But one thing we need to have in mind is that these J's are not really random quantity, or I mean, they are random, but they are not random IID. If you would really be doing a spin glass in the way we learn from those guys, when you try to model systems of magnetic systems with random interaction, the JRJs are just random independent variable. Here they are not random independent variable. They have been selected using a complicated, well, not so complicated, but using West prescription. So the J's are not totally independent. In fact, they are all correlated between each other in a subtle way because they contain information about the hidden assignment, the S star. Okay, so the J's are not random. I mean, they are random, but they are not random uncorrelated. They are not uncorrelated. Except from this is really a spin glass. Okay, so if you go back and read the paper of Surlat in '89 in Nature, he's using the same kind of construction to argue that the kind of thing that you do in coding theory when you try to code, decode, and information and process information is related to spin glass theory, and he's using that kind of example. Again, this is a terrible code. It's not a very good code, and no one would use this. But it's kind of instructive to think about it because it gives you a link between, you are doing in the two fields. All right, so this is, I think, interesting. And I think it's a very good example of what I was trying to say yesterday, that whenever you are trying to look into these problems, well, you are creating models that you know in statistical physics. Okay? Whether or not you can solve it or say something useful is another story, but it definitely appears. Okay, so all right, so let's try to solve the problem now. So imagine someone has done this, has taken a configuration of spins, choose the value at random, plus, minus 1. Then there's someone constructed this graph, computed all these values of J's, and then there's someone is giving me the value of J's, and to make our life simpler, there's someone also tell me the value rho. It could be learned, it's not a problem, but let's assume that it also gives me rho. Okay? Now my task is to decode, and as we have seen yesterday, the best thing to do is to consider the posterior information, probability, which is given by the statistical physics problem. And what is my best estimate for those guys? That's also something we discussed yesterday. The best estimate for S, for all Si, will be essentially the sign of the magnetization. So I will use the statistical physics notation. Okay, the magnetization of which model of the spin glass problem. Right, so if you have a practical mind, you can already forget everything I will say from now on and think, oh, that's great. That means that whenever I have to solve a problem like this, I just have to write the Hamiltonian, write a Monte Carlo code, and let it run for long, and you will be right. And that's a very good way to solve this thing. If you have a good model, it's a very effective way. And I mean, if the model is complicated, that's even the only way you can do things, because what else are you going to do than doing a good simulation? All right, but what I want to do here is not only solving this problem for an algorithmic point of view, because I don't think this model is particularly interesting from an applied point of view, but I think it's very instructive to see what is going on when you try to reconstruct. And I want to motivate the appearance of phase transition in this process. So let's try to approach it in a maybe more theoretical way. All right, so by the way, I wanted to say this, a spin glass problem defined on a random graph, it's called the Viana-Bray model. Because it was introduced by Viana and Bray in 85. Right, so you might complain that we hardly do new stuff here. I mean, this is kind of old stuff. And it's true. I mean, in many ways, I'm just taking old stuff and trying to make it look new. And I think it's basically how science is done most of the time. And the main difference here is that that was really computing all that for random J's, right? And our point here is that our J's are not random and they are created by this process. That's the only difference with what they have done. All right. So now let's do what Lenka did. Okay, so we have this problem. It's on a random graph. Let's assume that n and m are both large. All right? Large. In fact, they are large such that there is a constant c equal to 2m divided by n. So both go to infinity, but they go to infinity such that c is finite. So they grow with the same order, if you want. So this is exactly what Lenka did when she created these random graphs. This is a random graph with average degree c. If you take n node, m link, and then n is large, n is large, such that the ratio is finite, actually the average connectivity, simple exercise, is 2m divided by n. So we have a very large random graph. Also, Lenka told us that random graphs, they are essentially tree-like. I mean, if you look at a single node, up to finite distances, in fact, up to logarithmic distance, with large probability, it's a tree. So if it is tree, we can, well, apply techniques that works on trees. And in fact, we can use belief propagation, and that's what I'm going to do now. I will just use the equation that she gave us and use them to solve the model. All right, so let me show you how it's done. So first of all, in this business, when you try to solve a model, you usually draw what is called a factor graph. So these are the variables. So there are n of them. 1, 2, 3. So this is S1, for instance, S2, S3. These contain the constraint, or the so-called factor nodes. There are m of them. Okay, and in our case here, the constraints are just telling us something about two variables. So for instance, this one is connected with these two, and it's telling us that there is a probability factor J2, 3, S2, S3. All right, so let's make a simple, okay, so for instance, this one is connected to these two. All right, so in that case, since I have only 3 spins and 4 links, if you want, so this is a proxy for saying that these two are connected by a link. It's certainly not looking like a tree, but I don't know to write an infinite graph, so I usually draw a graph with 3 nodes and 4 links, because that will be enough. Now we do exactly what Lenka told us. He said, well, if you want to solve that kind of problem, what you have to do is to use message passing. You can use this belief propagation. So I will try to use the same notation. So you have message going from factor nodes to variables, which were psi mu to I of Si. And this is essentially telling what is belief of this factor nodes over this variable. And you have also messages going from variable to factors, which we call chi, I to, well, I don't know, mu of Si. Okay, and what are the equations of belief propagation? Belief propagation is telling you how these two are connected. And they're connected in a very simple way. The chi is the product over all incoming message. So all product over all gamma in the neighboring of I, which are different from mu. This is what the notation means. All the gamma that are in neighborings of I but are not mu, of psi, gamma to I of Si. What about this one? All right, that's very proportional in both cases. Well, this one would be equal, but what is this one? This one will be the integral over the product of all j in the neighboring of mu, which are not I. You integrate over all Sj. Then you have well, you have this thing that I don't remember how Lenka called it, but there is a probability distribution that depends on the spins, and you have the messages. So, chi j to mu of Sj, and you have this probability distribution that depends on mu. So in our case here, everything is simple, because if you look to one factor graph, the set of all variables, so let's say that we compute the message sent from this guy to that guy. Well, the set of all variables which are connected to him and which are not 3 is just another guy, right? Because every square here is connected to only 2 variables. So that means that this complicated equation is very simple. It's actually the integral of a. So let's say that you have something which is connected to I and j, and you want to send the message to I, you just have to integrate over Sj. And in fact, this integral is not even an integral because Lj is just plus or minus 1. So plus or minus 1 of kj to mu Sj. And the probabilistic interaction is also very simple. It's Jij, Si, Sj, beta. So this is it. You can just run this algorithm like this, and it would work. Now, it's not very practical here because, well, I mean, it's actually not practical at all because I write it as, well, there is a probability distribution here. Now you compute a new probability distribution, and from this new probability distribution, you compute a new probability distribution, and so on and so forth. And, well, it's not really enjoyable to work with probability distributions. It's actually better to work with numbers, right? This one is, yeah, they should be, which one should be? No, these two should be the same. You are complaining about these two? Yeah. Because I'm sending the message to this guy? All right, mu prime. My knowledge of Greek is limited to mu and gamma, and I'm already using epsilon and rho. Oh. I could be using upsilon and whatever. All right. Yeah, you're right, of course. All right, so the point is we don't like to work with probability distributions. However, remember that Si is plus or minus 1, right? And a probability distribution on a binary variable, actually plus or minus 1 is not really binary, it's Rademacher if you're in statistics. So on a Rademacher variable or on a spin variable can be parameterized with one number, as we have already discussed, which is a field. Okay? So in case you are working with spins like this, it's actually not a good idea to work with those, but it's actually a better idea. Actually, what I want to do now is to go from this to a equation that looks like physics, because that doesn't look like physics. Okay, so it's a bit tedious. It's not hard, it's a bit tedious, but I want to do it because then it gives a sense of what this equation look like in a familiar setting. All right? So instead of working with these two, I will be working with a field representation. All right, let's change color again. I will use this dictionary, chi j to mu of Sj will just be something which is proportional to exponential Sj times beta Sj times, I think I called it h, j to mu. And the other one is proportional to exponential beta Si, and I call this one u j of mu to I. So what I want to do now is to rewrite this algorithm, which is written in terms of this probability distribution. So this equation, or let's give it a name. Let's give it the same name I have here. One and two. Okay, this is one, this is two. So I want to rewrite 1 and 2 in terms of these things, which are just numbers. Because then I can just iterate things, right? If I say, okay, there is this set of numbers, now you compute this new set of numbers, and so on and so forth. That's a very well-defined algorithm, and it's less abstract than computing things in terms of probability distributions. Okay, how do I do this? All right, let's start by the simplest one. Let's look at 1. So for 1, it's easy. Equation 1 is telling us essentially that when you take the product of psi, you should observe chi. Okay? Notice that it's proportional, which means that everything that is in the normalization, I can disregard it. Yes?
Why do you think the distribution is 400?
It has to, because this is a probability distribution in terms of S is equal to plus or minus 1. So whatever it is, I can write it this way. It's just a parametrization of a distribution over a plus or minus 1 variable. Right? So it's not even an ansatz. It's just true. All right, so let's do the equation 1. Equation 1 can be written very easily in this form. In fact, equation 1 is just telling us that h from I to mu prime is equal to the sum over all gamma in the neighborings of I, which are not mu prime, of u of gamma to I. Right? I mean, this is essentially a product of all those guys. Then if you take a product of exponential, all these things adds up. And so if you want to have this correspondence, you just have to have the h are the sum of mu's. All right? And if you worry about the fact that I'm disregarding normalization, you are right. Please do it correctly, and you will see that this is actually the correct solution. All right, that looks better. By the way, this algorithm here, which we called belief propagation, is also known in coding theory as a sum product algorithm, for obvious reason, sum product. It's really interesting, because if you look at the literature of this thing, I mean, the people keep on rediscovering this algorithm. I mean, in coding theory, it was introduced by Gallagher, who was a student of Shannon, who basically developed the best code and the best algorithm, and everyone forgot, and then it was rediscovered in in the 1890s around the work of Surla and other people. And then McKay wrote this fantastic paper saying, oh, all this decoding stuff that you do, it's the same as belief propagation, which is something people do in artificial intelligence. And then later on, they say, oh, yeah, but isn't it what Geiger was saying? And then the physicists came and said, but come on, I mean, this is what Bethe was saying already in the 30s. So, yeah, interesting that everyone discovering the same thing. Maybe we are not, we are all clever in the same way. I mean, no community is more clever than the other one. We just do the same thing with different names. All right, let's look at the second one. The second one is a bit more tricky. So the second one, first of all, okay, let me take a bit some space. All right, let's look at this. Here what we find, if we actually do the sum, is the fact that psi mu to I of Si, well, let's do the sum. So this is just exponential of beta Sj, j exponential of beta Sj. The chi is with h of j to mu times this beta Si Sj Jij. All right. Now if we do a sum, we have exponential beta h. Let me drop all these indices, otherwise I will get crazy. H plus J is I plus exponential beta. Well, exactly the same thing actually. Right, and this is twice proportionality here. And it's the hyperbolic cosine of h plus jsi. That's jj if you want, and this h is mu. I will need this. I'm sorry? Yes, proportionality constraint explicitly depend on those guys.
Sorry?
They do actually.
This is not exactly equal.
This is equal. You all do the exercise, but yes, it is equal. The point is that if you do this, the normalization of this guy, you will have to recompute it every time. So well, do the exercise. I mean, it is equal. It's not a problem. All right. Now that I wrote this, what I want to write is what is psi plus minus psi minus divided by psi plus psi minus, right, with this notation. You see that this is nothing but hyperbolic tangent of beta u, mu to I. Right, that we know from this. Right now, we can write this thing on the side. So it's cosh h plus j minus cosh h minus j divided by cosh h plus j plus cosh h minus j. So it doesn't look great. I mean, you could use this actually directly, right? This is telling you how to compute the new value of u given the value of h. So this is a recursion, but there is a nicer way to write it. And what you have to do is to write that the cosh of a plus b is equal to cosh a cosh b plus sinus hyperbole a b. You write this here and you have some amazing simplification, and it looks much nicer. It looks like this: hyperbolic tangent of beta gij, hyperbolic tangent of beta j to mu. Okay, so this equation here can be written like this. U mu to I is equal to the invert hyperbolic tangent of hyperbolic tangent of beta gij hyperbolic tangent of beta h j to mu. All right, that looks nicer, I believe. I mean, that looks exactly the kind of thing you can put on a computer. Right, each of these messages here is parameterized by one number. Then you can iterate this equation and wait until you reach a fixed point. Once you reach a fixed point, then that's it. I mean, you have found the good value of h and u. And if you want to compute what you really wanted to compute, that is the magnetization. After convergence, you can compute the total field acting on I, which is just sum over all gamma in the neighboring of I. This one, all of them, u gamma to I. Once you know this, you can compute mi, which is the magnetization, which is nothing else than hyperbolic tangent of beta hi. And from this, you compute your estimate, which is nothing but the sine of mi. Et voilà, this is the way you apply Billy propagation for this particular problem. And what I did here, I mean, just to rewrite this equation in a nicer form, is something you actually have to do every time, because it's kind of crazy to work with the distribution and with the general equation. So for each problem, you have to work a bit in order to put them in a way that is nice. But otherwise, I mean, it's very simple. You iterate that, compute the total field, then you have to estimate for the magnetization, and then, well, you take the sign. So there is a little problem here, which is, what do I do when the sign is 0? Because, for all what we know, we could be in a paramagnetic phase where the magnetization is 0 for a given variable. In that case, this is telling me that my estimator doesn't know what to do. And basically, you will be choosing randomly. I mean, it's never exactly 0, so maybe it will be plus or minus epsilon. And, yes? How come do I get? I didn't get paramagnetic result, because HIs are not uncorrelated, right? They are coming from a complicated stuff. If you want, even if you do a Monte Carlo simulation in a very complicated model, you can it looks like mean field, but this is again a triviality in the sense that even if you compute the true magnetization of a true model, you can say that, oh, this model looks like this spin here is uncorrelated with the rest of the world and is behaving with a given field. okay? So this is how it looks like, but these h's are not variables which are, independent one to the other. They are coming from a very complicated process. So you have computed somehow, if you want, it's a kind of, reductivism approach in which you take the full system and you can break it down into effectively something that looks like each spin having an effective field on it. But the effective field is a very complicated function, right? Of course, if then you say, oh, it's the same everywhere, and then that looks mean field, but this is not mean field. Okay? So these equations are actually exact on a tree, and we know they are asymptotically exact on a random graph if the graph is large. This is giving you the correct marginal, the correct magnetization. Right? Of course, you could have done all this by Monte Carlo, directly done this, but it takes longer. So what happens if you do this now? So let's do it. You create a large random graph, I don't know, billion nodes, it's easy in the computer. We run this algorithm. We run belief propagation, good. We converge. We have the estimate of the magnetizations. Then we have the estimates of those guys. And what do? Then we can compare how good we are, right? See how different the SI hat are from the SI star. We can see how good we were. Of course, if you are really trying to do this, you don't know the SI star, so you cannot really do that. But if you are just playing with the problem and you created the problem and you want to see if you did a good job, you can say, okay, now let's see if our algorithm is good, right? So let's do it with, I don't know, epsilon rho fixed. So let's take a number. Let's say that we use rho equal 1/4. So 25% of the guys were lying. And now let's see what happens when we change the value of C. So of course, the larger C is, the better it is. Because it means I have asked more and more and more and more people their affiliation, if you want, or the product of their affiliation. So it's intuitive that if C is very, very large, well, I should have a good information. So I should be able to do a good job. If C is 0, well, I have not asked anything to anyone, right? I don't have any information because M is 0. And so probably I will do a bad job. All right, so let's plot here what happened if you try to apply the algorithm and you plot here the fraction of correct answer, or if you want, the sum of delta Si hat Si star divided by n minus 1/2. Why minus 1/2? Well, because a random guess is giving me already 1/2 of them. Okay, so I want to have something here which is 0 when I'm doing a random guess. Right? And also, let's take the absolute value here. Well, no, that's fine. Let's forget about the absolute value. So let's do this. And this is how it looks. When n is large, if you do a very, very large system. In fact, it looks like that. But as n is going to infinity, this thing goes to 0, and you start to have a sharp transition. So what is going on here? So there is a sharp transition here, at the value C star. And if C is smaller than C star, that is, if I didn't ask enough people their affiliations, what I have done is no better than a random guess. In fact, only half of what I'm saying seems to be good. And if you look, why is it so? It's because, in fact, you are in a paramagnetic phase. In this system, in this region where C is smaller than C star, then we will see how to compute C star, all the mi are zeros. So by taking a sign of zeros, basically you are fitting to, if you do that in a computer, you are fitting to numerical errors in the long double implementation, right? So essentially, either you get a nan, or either you get a random number, but you are doing a random guess. So it's kind of logical that you are just getting 0. So what does this mean? This means that even if you solve exactly the problem, the inference problem, which we did, if you don't believe me, you can also do it with Monte Carlo, and you will find the same. Even if we do the best we could, well, the best we could is still telling us that we don't know enough to say anything about the hidden assignment. Okay, that's life. So that will be a parametric phase in the language of physics, and we call this impossible region. Because in this region, there is no way we could say anything about the hidden assignment. So I think this is interesting, because maybe for a physicist it's kind of intuitive, because you think, oh yeah, well, sure, phase transition, and but I think it's not so intuitive if you think about it, because there seems to be information in this process, right? I seem to be collecting information about all those S's. Yet, if C is smaller than C star, well, this information is not enough to say anything about the groups of the origin guys. Yes?
So what does this have to do with percolation?
Good point. The percolation threshold is somewhere there. So you are way below percolation. Of course, before percolation, the percolation is obviously a lower bound on this, right? Before percolation, of course, you're not percolating the information everywhere. So,
but once you percolate it,
it seems, but remember that there is this guy. Some people lied to you. Okay? So if you want, you send the message to the on the percolation on trees, but some of them are wrong, and that's enough to screw your estimate.
So I mean that effectively it doesn't percolate because
yes. Right? And of course, we should expect that when rho is going to 1, it should have something to do with percolation, right? I mean, that would be really cool.
And also, so to get this graph,
doesn't have to be true, but
to get the graph, you need to do computationally, or?
Well, the graph, you see, it's all the way I've created the system. The way I created the system is by. Oh, this one. I will tell you how to do it analytically in the large n limit. Otherwise, yeah, I mean, you have to do to solve that kind of thing for many. So you create a system with that many. So you take 1 million variables, then you create a graph of let's say 2 times m something that gives you a graph here. You apply this algorithm, you compute the solution, when you find the estimate, and you see what you got. So. I can do it analytically, and it depends what you call analytically, actually. I can write a self-consistent equation using this. I will do this at some point, maybe not today, but maybe tomorrow. And then you have a closed equation, but it's still a complicated equation. You have to solve it numerically. But that's fine. Solving it something numerically is not so hard. So yes, you can get a numerical estimate for this in the large n limit. And you can prove rigorously it's correct, actually. We have theorems about this. I'll give you references. So I think it is interesting that there is this impossible region. You know, I mean, you would expect percolation, but no, it's not really percolation. So it's something interesting. And then, of course, if C is larger than C star, so there is a sharp threshold, right? When you start to have enough information, when you ask enough people, well, you have a second order transition, you start to be able to make guesses better than random. And as C is getting larger and larger, you are approaching 1. At some point, of course, you are making a very, very good job of guessing the group of everyone. The fact that it is 0 here and 1 when you have a large number of information, I don't think this is surprising. I mean, this should be expected. What is interesting is the fact that we have a sharp transition. So in this case, call this the easy region because, well, it's easy to get a good reconstruction. well, good. This is the best we can hope for, right? And we get it. And it's good in the sense that it is at least better than a random guess. Say that again? It actually saturates to 1, but you have to go to values of C's which are growing like, you remember this is log, you need C to grow like log n at least, something like this. I'm sorry? I subtracted a 1, yeah, it's something like this. Good point. So I should divide by this. Good point. All right, I should multiply by 2, if you want. All right, so it saturates to 1 eventually, but in order to do this, you need to have a very large number of observation, and it goes like log C. There is actually a rigorous proof of the scaling by Emmanuel Abbé in Princeton, who repeated all this computation that I'm discussing now in the context of exact reconstruction. He wanted to know what is the exact number of people you need to ask to have a perfect reconstruction. All right, so these are these two regions. It's second-order phase transition in the context of physics, and I think it's interesting here because it's telling us that whenever you do this inference on graph, well, you have interesting phase transition, and more than that, it's a phenomenon that if you don't have enough information, you cannot tell anything. Right? So it is also something we should remember for people in data science. You know, you are trying to do a lot with what you have, and sometimes you are doing something totally wrong because you are extracting information where there is no information. For instance, if here, instead of using this estimator, which is the best one, the one where I'm just trying to compute the equilibrium magnetization, and then I'm taking the sign, I would have been using something else, like the map estimator, which in that case is saying, compute the ground state of the problem. I would have found a ground state. Well, to be honest, actually finding the ground state is hard here. It's an NP-complete problem, but let's say that we can do this. You found the ground state, and now you are happy, you think it's good, right? Because you solved the maximum a posteriori probability problem. And so you are saying that you go to your boss and you're saying, this is my estimate of the belonging of all these people. Except it is wrong. It is wrong because we computed here what is the best possible overlap between, you know, when you are using the best estimator, and it is 0. So here there is something interesting. If you do a map, if you try to find a ground state, you always find something.
Even under that prior that is the judge.
Here, my prior was the fact that everyone was equiprobable. But that's true. That's the way I created the problem. Right? This is not a practical problem from reality. This is a problem I created. So it's true that I actually selected the configuration randomly. In fact, if you think about coding theory now, in which I'm just saying that I want to send one of the 1 to n word, this is actually true. I mean, the prior is correct. Right? I'm saying that all words are equiprobable. This is a good construction. Okay? So in that case, all this thing that I do here is what we call base optimal. This is the best thing we can do. I mean, it's true probabilistically that this is the best guess that you can get, and this is telling us the best guess is still a bad guess. Now, if you don't do this, and instead you are saying, well, I will do a map estimate. The map estimate will give you the ground state of the problem, and you have no way to know if it's good or not. Actually, this is not true. There are ways how to check this. There is cross-validation techniques. But I think that there is something interesting here is that, you know, there are regions where a lot of technique will give you something. It will fool you into believing you learned something about the problem. But the rigorous solution, because this is rigorous actually, is telling you that there is no way you can learn anything. So anything that you think you have learned is an illusion. Right? And there is a sharp transition like this in essentially any kind of, you know, learning problem that you can create and study. You always have a kind of behavior.
So I guess that was the difference between map and what we're doing here is whether you take the prior to be a Gaussian or...
No. The difference is the following. when you write your P of S given J, psi Sj. Okay? So remember that beta here is given by rho, so we know it. So what we have done here is the best possible thing. It's computing the exact magnetization at finite temperature. Map would say something else. Map will be take S, which is the argmin of the whole configuration on the Hamiltonian. So if you want, it's the argmin of some of. So it's really the ground state, is the configuration that minimizes the energy. Okay, so there is always a ground state here because it's bounded. I mean, there is a finite number of elements. So there is a ground state. There is a configuration which is better somehow than the others, right? Except if you are just using map, you're fooling you into believing that you have learned something. And why? Because you're not taking into account entropy here. Okay?
Is this average over disorder in your random network?
Good point. When the network is super large, you can actually show that averaging of the disorder doesn't change anything. There is a self-averaging properties. So it will look like that, yes. That you average or not.
You can construct a highly connected graphs, but you won't learn anything because you can.
Wow. Okay, this is what you get with high probability. Then there are, of course, a lot of funny things that you can get. There will be small regions highly connected where you will have some Griffith singularities, and you could learn things that maybe, you know, if you look at neighbor X guy, you could have, you know, these two are, I mean, if two guys are connected, you already know that they are probably in the same group, right? Actually, with probability 1 divided by 4, they are in different groups. So you know things. It's not true that you don't know anything, but I'm trying to learn about the global information, right? And that you don't get. Now, of course, since you can do this on every single graph, for exponentially rare graph, this picture will be wrong, right? This is true with high probability. Yes?
Here, instead, you chose M to be still with M, but if you have a fully connected graph, basically you have every.
That's my next exercise.
Okay. And then here you can just let someone ask it, or
you can do that kind of stuff with mean field in that case.
You can just write beta like Gij and J.
Yes.
And then you just iterate, and then in terms of is there a threshold there?
Yes, but you have to state the problem a bit differently. You have to, in order to have a threshold in that case, you need your rho to be 1/2, so 1/2, minus something which is 1/√n. In this scaling, you have a transition. So I will be discussing this problem just next because it's also very instructive. But otherwise, if you keep that scaling for the probability of lies, well, if you have as I told you, when the connectivity is of order log n, you have a perfect reconstruction. You're asking me what happened with probability of order n, well, you have a perfect reconstruction in that case, right? So if you want to have something non-trivial in the fully connected limit, you really need to have rho close to 1/2, like almost, you know, the probability, everyone is ever lying or saying the truth, so you don't have information, your information is very small. All right, so what I want to do now is to try to compute the C star. And it will be easy to compute C star because Taules computed it, and Castel and Stingum computed it, and even more recently, Lenka computed it. Because after all, what is this? Well, this is a second-order transition from a paramagnetic phase to a phase where every spin starts to align, well, not every, but most of the spins start to align with their hidden value. By the way, this is exactly what Lenka called the planted model. I mean, I have created the system starting from a hidden configuration. It's very much connected to what she does. And so we can do this by a stability analysis. The stability analysis should be done this way. Imagine you have a field that starts to go in the good direction, pointing to the correct assignment. If you do an iteration, is this field growing or is this field decaying? If it grows, it means there is an instability, and if you run the algorithm, it should go in this direction. If it decays, it means the paramagnetic phase is still stable towards such perturbation. I mean, simple 101 dynamical system computation. So there is a trick to make it even simpler, and I will do it now. All right, so let's look at this problem that we are looking at. There is an Hamiltonian here, which is nothing but that. Now there is a way to gauge transform this problem into an even simpler one. This is how it works. First of all, notice that if you replace Jij by Jij to I to j, and Si by Si to I, with tau I with I equal 1 to n is a variable which is plus or minus 1s, this leaves the Hamiltonian invariant. Right? Because here we'll have j times tau I to j times Si to I, Sj to j. Then I have Si twice, so it's tau I squared, and tau j will be also squared, and since it is a plus or minus 1 variable, it's 1. So the Hamiltonian is invariant under such transformation. Right, so this is a gauge transformation. It leaves the Hamiltonian invariant. In this case, it was introduced in spin glass theory by Gérard Toulouse in the 80s, can't remember when. And it was exploited most famously by a Japanese physicist called Hidetoshi Nishimori. Nishimori has done fantastic things using this gauge transformation. And in fact, a lot of things that we are doing here is using what we call the Nishimori symmetry. It is following his work. So this is true. Now, there is one gauge transformation which is very interesting. Let's use tau equal S star. Of course, you cannot do this if someone gives you the problem and you try to solve it, you cannot do that, I mean, because you don't know S star. But this is not what we try to do here. We try to analyze what is going on, right? So as theoreticians, we can do this. Let's try to do that. And if we do this, we still have the same problem here. The Hamiltonian is invariant, so all the configuration have the same energy. So everything you want to do here will be exactly the same, right? Doesn't change anything to the problem. However, it makes two interesting changes that are making our life simpler. First of all, the new j's, right? They are equal to the old one times S star with the star values. So why is this nice? Because this guy here, it was equal itself to Si star, Sj star with probability 1 minus rho, and minus this with probability rho. That means what? That means that Jij star, prime of the new problem after the gauge transformation is just 1 with probability 1 minus rho, and minus 1 with probability rho. So after the gauge transformation, we have a very simple problem in the sense that now these j's that before were correlated in a very hidden way, so it was kind of hard to analyze, but not so hard, but you would have to work. Now they are just random independent quantities. If the people lied, well, it's minus 1. If this pair told the truth, it's 1. And now it's just random independent. And of course we like independence because it makes our life much simpler. All right? And what happens to S star in the new problem? So what is S star prime, if you want? Well, if you look to S star I prime, it's Si, so we use this rule, star times Si star, and it is 1. So I have gauge transformed my problem into a problem in which the hidden assignment, the one I'm trying to find, is just the set of all spin equal to 1. Okay? So that's simpler, because now asking if we are able to do something, if we are good at reconstructing, is the same as asking, do I have a ferromagnetic transition? Because if I have a ferromagnetic transition, it means the average magnetization is positive, and so I have no good overlap with the hidden assignment. Right? So it's certainly simpler to compute this, because it's, this is what we learn in physics, how to compute ferromagnetic transitions. So this is nice. We just have to compute ferromagnetic transition. So after the gauge transform, this easy phase is just the ferromagnetic phase of the Ising model. And this is also nice, because now it's a problem with J chose randomly. Randomly, but most of them are positive. Which is good, I guess, because if we want to see a ferromagnetic phase, that is the appearance of a positive magnetization, well, we better have J's a bit ferromagnetics, right? I mean, if all of these were probability plus or minus 1 with the same probability, we would not expect this. So it's much simpler to study this problem after the gauge transform. Right, so let's do it. So I have this equation here, that's good. We'll do the stability analysis towards a ferromagnetic perturbation, and that means the following. I should ask what happens if, let's say that all these U's, okay, so first of all, what happens in the paramagnetic phase? In the paramagnetic phase, magnetization are zeros, that means that the local field acting on each spins are zeros. Okay, so there is a paramagnetic fixed point, which is exactly the same thing that Lenka described when she described its fixed point with 1/q everywhere, right? So it will be a fixed point where all the psi's are 1/2, and this size, and the size and the psi's are all 1/2. And to have 1/2, it means that when you use the exponential representation, the field is 0. So the parametric fixed point means all h's and all u's are zeros. Now you want to know, right? Now we have done this nice gauge transform, so this is just a ferromagnetic phase. That we plot here is essentially the equilibrium magnetization, right? So it's really statistical physics, simpler one. And we ask when is going from here to here, so it's something you will get from a perturbation in which you start to have fields that are a bit positive. Let's add that these u are not 0, but epsilon, but all positive. Now you compute the new h. From the new h, you compute the new u's. And now you just want to see if the new u's are a bit larger than before. If they are a bit larger, that means that there is a perturbation into developing ferromagnetism. Or if you want, that means that the susceptibility is infinity, and you are not in the parametric phase. If they are decaying, well, that means the paramagnetic phase is stable. Simple computation. All right, so let's do it. All right, so imagine that your tree looks like this. It's always good to think about something that is actually doing an iteration. That's not what I wanted to do. Yes. All right, so let's look at the portion of the tree. So there are messages that goes here, right? So these are the these are the u's, if you want. Okay, and I will put them small. All these u will be, I will say that we are telling this guy an information. We are telling him, look, I think you really want, you might want to be ferromagnetic. And now we want to see what this guy is sending here. Right, so these are the u's at generation t, if you want. And here, well, these are the u's at generation t plus 1. right? And so we want this guy to be small, but positive. So we have epsilon mu to I, which is positive and small. Let's assume they are all the same. All right? So now, here, what we have to do is to compute the value of h. H is the sum of the incoming u. So here there is, okay, this guy is I, this one is gamma. So here we have h, I to gamma, that will be essentially the sum of all this guy. Okay? So, on average, I have, so if since the graph is random, and the average connectivity is C, the average number of neighboring guys that send me a message is C. So this will be on average equal to C times epsilon. All right, so let's write it a different way. I'll write here that we have U from mu to I, which is epsilon. Okay? So the field which is sent there will be C times epsilon. Now, what is the value of U gamma to, how do we call this one? L? Well, we have to apply this, but it's not so hard because h is small. So hyperbolic tangent of something small is just itself. Okay, and so we have hyperbolic tangent of beta j times beta h, but this is small itself. So the arctangent of this is also small. So when you do the linear computation, that will be just you know what? There is a beta here. That will be telling you that the new u here will be hyperbolic tangent of beta gij times beta h, but the beta cancels, so times c times epsilon. So that means that when you go from here to here, your perturbation has been multiplied by this factor. Now, if this is on, so of course, you see that that depends on the value of j, so we would have to average this over the whole graph. But the point is, either this is large, in which case, well, the perturbation will blow up. Either this is small, in which case the perturbation will basically have no effect because it will vanish. Right? So that means that we expect a transition if, let's average over all graph of the graph, so the j's are different everywhere, so we have to integrate over p of j, hyperbolic tangent of beta j, times c is larger than 1. Or if you want to include the critical point, right? Or even, yeah, c star. Let's define the transition this way. All right, we know what is the distribution of j. J is equal to 1 with probability 1 minus rho. It's equal to minus 1 with probability rho. So this can be written as tangent beta times 1 minus rho plus tangent minus beta, but this is minus hyperbolic tangent of beta. Times c star is equal to 1. There is a rho here. Okay, and so this is hyperbolic tangent of beta times 1 minus 2 rho. C star is equal to 1. Now, you have to remember that beta was not just any beta. I mean, I know it plays a role of temperature here, but this beta was actually something that came, which I erased stupidly. It was here. it came from the construction, right? When I did this Bayes formula, beta was pretty much related with 1 minus rho. And in fact, if you remember, hyperbolic tangent of beta was exactly 1 minus 2 rho. So this condition is 1 minus 2 rho, C star is equal to 1. And it means that here we expect that C star is 1 minus 2 rho squared. And if you want the value, when rho was 1/4, 1 divided by 4, this is 1 minus 1/2, so it's 1/2, squared is there, so this is 4 rho equal 1/4. This is a non-trivial result, right? This is telling you that in the large limit, if you want to have enough information to say anything about the assignment, you need to have m, which is equal to 2, all right, so sorry, m divided by was c, so you need to have m 2, okay, so you need m should be larger than 2n if rho is equal to rho 4. I find this interesting. I mean, it's non-trivial statement. Okay, you can fill it with any probability you want here. And that's really interesting. If it's less than 2, you're not able to say anything. It's a bit more than 2, then it fastly grows towards something in which you have very few number of errors. With a sharp transition, and we're able to compute where it goes. Right, I'm getting out of time. Let me give you 1 or 2 references here. Well, yeah, I have 3 minutes. So how much of this is rigorous? Pretty much everything, as a matter of fact. So the transition here at C star was proven recently by many work, Manuel Abbé in Princeton, Lelarge, myself, Lenka, and Assad in Paris, using the probability, some random matrix theory and something called the non-backtracking matrix. So the fact that there is a transition between an impossible to an easy region is rigorous. Then the fact that belief propagation is optimal, and that if you do this and compute this curve, this is actually the best thing you can do, is also following a recent paper that we did with Amin Koja-Oglan and Will Perkins. So this is rigorously true in the large n limit, all this picture. Okay, so it's time, I think, to conclude. I wanted to say something else, but it will wait tomorrow. So I think there is something to learn here, and it is that when you are trying to do, so for coding theory, people know this. I mean, in some ways, this is a statement of Shannon theorem, that if you have too much noise, you cannot transmit anything, and if you don't have otherwise, you can transmit something. It's very similar to it, and this is why Nicolas Surlas studied that kind of models when he made this analogy with glasses and coding theory. But if you think about it as a learning problem, this is telling you that the size of the data set matters. And it matters not in the sense that you get better results if you have a larger data set. I mean, that, yeah, of course it's true, but that's a triviality. But it matters in the sense that if your data set is not large enough, you are just doing n'importe quoi, as we say in French. I mean, it's just random thing. You are just fooling yourself into thinking that you are learning something. That is, you know, interesting. I believe this is actually the case in many published work, unfortunately. And, people are doing n'importe quoi, but most people know it, actually. And if you are doing learning, you know, trying to make sure that your predictions are accurate is a very strong problem. And I think it's nice that the statistical physics construction is giving you example where you can see region where you can fool yourself and region when you can't. And philosophically, there is a nice thing to say here is, if you read these days about the success of deep learning and what people can do with neural network, I mean, neural network is a very old technology. I mean, all these multi-layer neural net, they are very old. I mean, they were invented in the 70s and the 80s, and people tried them, they were not working. And the reason why they work now, how many reasons why they work now, but pretty much is because of the size of the data set. I mean, now you have huge data set, and that's why you can actually train them. And in fact, if you try to learn, to do deep learning and all that with data sets which are too small, you are not doing something very good. And it's my belief that this is again something that is reflected in phase diagram. And there is somehow a phase transition in these learning problems. You need to have a large enough data set in order to learn something. Otherwise, not only you are not learning something good, but you might be learning something terrible. All right, I will stop here, and thank you for your attention, and tomorrow we solve another problem.
More than half the people like you, if rho is greater than half, then you never have any.
Well, when rho is okay, so all this is basically with rho smaller than 1/2, because otherwise, if rho is larger than 1/2 and you know it, you can do a transformation and go back to because if rho is bigger than 1/2, if you think about it, most of the people are lying to you. I mean, it gets really hard to say anything, right?
So there's never any easy reason.
Well, if everyone is lying to you, actually, probably there is the same thing in symmetric. I think I should think about it. But if you know that everyone is lying to you, then most of the time when people are, you should just change everyone to telling you j into minus j, and you are coming back to a situation where less people are lying to you. So if there are more than half people lying to you, it's the same as less than half people not lying. So it's if everyone is lying to you, then it's easy, right? It's just the same as if everyone says the truth, because it's, haha, you are not friend. Well, okay, I know.
If exactly half of the people lie to you.
If exactly half, then you're screwed. This is really a spin glass, and the sister is diverging.